So it is my pleasure to welcome Professor Jean-Pierre Fouque from Department of Statistics and Applied Probability, University of California. He will be giving a talk on mean field game and mean field game control, Q-learning. So please, you start.
Okay, thank you so much. I mean, this is a nice opportunity. Thank you for the invitation. It's a bit early here in California, 6:30 or 6:38. You have to excuse my voice because I got COVID, by the way. I'm confined and I have COVID, so I have like a cold and a sore throat, no fever, so hopefully everything will be fine, but I'm confined in my bedroom. So no risk for you. Okay, so I want to tell you a little bit about something we did recently with my co-authors, Andrea and Julie, who was a PhD student now working at Amazon, Mathieu Laurière, who is now in position in NYU Shanghai. And we looked at reinforcement learning, or Q-learning, for being more precise, for mean field game and mean field control, and with some application to finance. So I want to go through that. It's a bit, there is a lot to absorb, so I will try to be as detailed possible, but I know that it's a lot of material to absorb at the same time. So if you have any question at any time, just interrupt me and ask. So basically, to make sure that we are on the same page, and I'm pretty sure that you all know Markov decision process in a finite state and action space, we go back to 62, Bellman, and so we look at the case of a finite space, finite action space. You have dynamics, so this is a probability to jump from x to x prime given that you took the action A. You have a cost function, so here we minimize things because we are thinking about finance. We minimize the cost. Usually in this area, we maximize a reward, but that's exactly the same thing. And so this is alpha is a policy. So I will be a little bit not give you many details on that. This policy can be randomized, it can be deterministic, can be stationary. As we go, I will make this precise a little bit. But basically, this is how you choose your action given the state. Okay, and the goal of the game here, and there is no game there. There is only one agent. The goal is to minimize over all the possible policies, allowed policies, is value function. The value function, so you accumulate all the way up to infinity with a discounting factor. You accumulate all the cost, and which depend on where you are and the action that you took, starting from a point X, and where Xn follows the dynamics given by this kernel P probability transition that I mentioned before. And so you want to minimize that. And in fact, we are not really interested in the value function itself. We are interested in the optimal policy, which I denote by alpha star, which is the argmean of this optimal value, right? So our goal is to find this alpha star. So for that, we have several approaches. One approach is to look at the value function itself and write an equation. So obviously, V alpha, when alpha is given, follows this sample equation where you have the first term. So this is to wake up the system, let's say, and then you are at position x1. You are at position x1, and you look at the value function from x1. You discount, and so this is what the value function should be satisfied for a given alpha. This is a Bellman equation for a given alpha. But what we are interested in is a Bellman equation for the optimal value, V star, and then you can prove that the optimal value satisfies by just taking the minimum here and following the optimal policy later on. So this is your Bellman equation, right? So reinforcement learning. So if you knew everything, if you knew the dynamics, if you knew the structure of the reward, then you try to solve this Bellman equation. In the case of reinforcement learning, we are in the case where we don't know those. The function f, we know the cost, the value of the cost, but we don't know the structure of the function f. we know the next position, but we don't know the dynamics. This is given by what is called an environment. And we try still to optimize and get the optimal policy by doing trials and error. This is the idea of reinforcement learning. And in our case, since we are in the case of finite space and action, this is called Q learning, and I will tell you what is this Q matrix. So the Q matrix is basically like a Q table. You have a row of each row is for any state X, and each column is for the action A. So that's, you can consider this as a matrix or Q table. And for a given policy alpha, what you do is you isolate the first step, the first decision. So this is the first decision that you know where you are, you know which action you take, the first action that you are taking, and then you accumulate all the costs in the future, right? So obviously this can be rewritten in terms of the Q alpha starting at X1. And so this is your equation for Q alpha. And if you take if you follow the policy from the beginning by taking alpha A equals alpha X, you recover the value function. So basically the Q table isolates your first action. That's the idea of this quantity. And now you want to look at the Bellman equation. This Bellman equation is derived, if you go back to Bellman in the 60s, by policy improvement. And this Bellman equation reads like this. So you get your optimal Q, which is the minimum over all the policy of this Q alpha, and satisfies this equation where you have the first action, and then you follow the optimal Q, but you take the optimal action, right? So, and obviously this V star will be given by the minimum of Q star over all the action. And one of the big advantage of dealing with a Q matrix or Q function and not the V function is that if you know Q star, if you find Q star, right away you have the optimal policy by taking the argmin of Q star. So that's one of the advantage of Q star. If your goal is alpha star, that's it's a better quantity than the value function. Okay, so this is a diagram that you see in any reinforcement learning textbook. You have the agent right there. You have the environment. The environment is what you don't know, the F, the dynamics. The agent take an action, gives that to the environment. The environment returns cost associated to the position and the action. It computed the next position. It passes that, it keeps that for itself. It's part of the environment. It passes this information, the value of the cost and the state to the agent, which given this, the agent make a decision, take an action, and then you go over again, and the agent will try to optimize something, right? So this is what is called the MDP, Markov decision process. So we do episode, everything is working by episode, you work by episode, and each episode you try to learn more and more and more, and that's the idea of Q learning. So you initialize Q, you choose an action. Usually, when I said at the beginning that the policy can be randomized, for instance, you can use an epsilon greedy policy, meaning that okay, you take the argmin of your Q, that's what you should be doing, but with a small probability, you will explore the state. And this is exactly what this epsilon greedy, for instance, policy is doing. There are other things that we do. You can use a Boltzmann distribution. You can use a lot of things and decrease the temperature. There are many ways to do that, but here is an example. So, but the idea is to explore. So you want to give a chance to your system to explore all the actions. Now you observe this cost. So observe meaning the value. Sorry. The environment is giving you the value of the cost. It gives you your next position, and then you update your Q like this. So this is the new Q. You take the Q from the previous episode, and then you have a rate. So this is very important. Raw Q, we have to focus on this quantity. This is a rate of update, and this is exactly what you want. This is the error that you are making by not being optimal. That's your Bellman equation. This will be 0 if you have the optimal action, so you don't update anymore. And you see that when you put that together, it means that you are updating going in the right direction. That's basically the idea of this updating. Now, this rate is 1 over 1 plus k. So this is not exactly k. It depends on the number of times you have visited X, number of times you have visited the action A, number of times you have been there. But it's 1 over 1 plus k, let's say, to some power omega q. And this omega q should be between 1/2 and 1. And this is due to the stochastic approximation that we will be doing in a minute. And these are the conditions for the Robbins-Monroe algorithm to converge. So this sequence should diverge, and the square should be square integrable. And that's exactly what this omega q is doing here. So this is our focus. We should focus on rho q in the next slides. So now, how do we understand the convergence of this algorithm? So you can define this operator on the matrix Q. So this is the updating operator, and that's how we can rewrite what is the updating. So you have Q at the next episode. You take the former episode, the last episode, and you update with this operator. This difference equation, if you think about episode in terms of time, so this is not the time of the process; it's the time of the algorithm, right? This equation is tracked by this ODE, and this ODE, of course, will converge to the fixed point. We assume that there is a fixed point here, and this fixed point will exactly satisfy the fact that this Q star, because it will satisfy that this is 0, and this is your Bellman equation. So the fixed point of this equation will satisfy, and that explains why this algorithm should converge. The only problem here is that this is an expectation. Yeah. As you see, you take a sum with all the possible probabilities, so that's an expectation. And we cannot do that because we observe only one trajectory. We are along one trajectory. We don't use the environment as a simulator. Some work says that you can use the environment as a simulator and estimate this expectation. We're not doing that. We go along one trajectory, and along one trajectory, we should be able to estimate this. So this is where the stochastic approximation enters. So instead of taking an expectation, you just follow the trajectory. But then if you work a little bit, you see that your updating is fine, but you are making a mistake. This mistake is a martingale. And because of the properties of the rho Q, this term will disappear in the end. So that is the basis of stochastic approximation. And this is why you need all this condition on the rho QK, the decay of rho QK. Okay, so I'm not too much insisting, but this is an important point. So now let's look at, so we are done with the classical MDP. Now let me introduce the mean field game. So the mean field game is the following. So first we have two things. We have mean field game and we have mean field control. So I want to make the difference between the two, because the goal of our work here is to design one algorithm which will be able to solve either mean field game or mean field control. And so and I will explain a little bit more the motivation that why I started this work. We'll explain that later on. So I hope so far everything is fine. There is no question. I can continue, but just interrupt me if you have. So mean field game formulation is the following. So suppose you have a mu hat. Mu hat is given. Mu is a distribution. Suppose the cost now depends on the distribution. Think about this: the distribution of the population. So now you have a population of agent. The environment has a population of agent. The environment knows the distribution of the population. It's supposed to be the distribution of the population. Then you take an action. You are the agent. You take an action, and you collect all your reward discounted up to infinity. And of course, you want to minimize that. And this X, your position, your dynamics, is again given by this transition probability, which again depends on the population. You start from a given population, and then what you want, this is a part of the mean field games, the Nash equilibrium, if you want, the fixed point, you want this mu hat to be the distribution of your own dynamics. not exactly the distribution of the dynamics in the classical min-phi game. Here we are looking at an asymptotic formulation in the sense that we want this mu hat to be the limiting distribution or the invariant distribution. I prefer to say limiting distribution, but in a minute we will see that it's equivalent to stationary distribution. So basically, let me explain. So first, just a remark is that since this doesn't depend on n, the control will not depend on time. It will be a stationary control. We are looking for a stationary control in a feedback form. So intuitively, you are an agent, you want to join a crowd which is already in equilibrium, and this is what you will do. This is exactly what you will do. And you want to find a Nash equilibrium so that when you join the crowd, you have no incentive to do differently as the crowd. That's a Nash equilibrium between you and the crowd. So this is an example of min-phi game. Have been many now. The work from min-phi game started in the 2006 with the work of Lasserie and Lyons in France and the group in Montreal, Malakern, Malamé, Wang. So this has generated a tremendous amount of work, and with many applications in many areas, and in particular in finance. You have application in finance. I hope I will have time at the end to show you a couple of applications, in particular, for instance, the trader's problem. When you have a trader who wants to liquidate a position, what is the best strategy? And you can learn that by what we propose here. So this is, and of course, the min-phi game is part of, you have many traders. You are among a lot of traders, and you are impacted by the distribution of the trade. So let me go back to application at the end, and so I need to speed up a little bit because it's a long talk in some sense. So this is our min-phi asymptotic formulation, and then you have the min-phi control asymptotic formulation. And I want really to focus on the difference between the two. Here, this is a real control problem. Let me go back here. Here, for mu at given, we have a control problem, but then you have a fixed point problem, right? So in overall, we are not solving a control problem. We are solving a min-phi game problem. For min-phi control, we are solving a min-phi control formulation because here, I don't give you the mu. The mu is related to your own action. So you have an action. We suppose that your action has dynamics, gives you dynamics, that this dynamics has an invariant distribution or limiting distribution. And this is exactly what you put here. So you give an action and you know exactly the distribution of the population. And you try to minimize that. So that is a classical control problem in some sense. And so this is called min-phi control because it depends on the population. It depends on the distribution, the own distribution of the dynamics. Or in other case, this is called Makin-Vlasov control problem because the distribution of the dynamics is included in the problem. And of course, the transition may also depend on your own law. So if you think about continuous time, this will be, let's say, the drift. The drift of your diffusion will depend on the distribution of the X itself. Right? So, and the mu alpha, again, this is asymptotic formulation. The mu alpha is a limiting distribution of your alpha. So I give you an alpha, let's say mean reverting alpha. There is an invariant distribution. This is the invariant distribution that you put here. Right? So again, the control is independent of time. And this is more the point of view of a central planner. You have a central planner who observes all the agents and gives the same alpha to all the agents. And that's why the mu will depend on your alpha because you have a lot of agents following the same alpha. So that's exactly the idea. And now you want to find the alpha, which is minimize the cost of joining the crowd for a new agent to join the crowd. Okay, so well, let me go back a little bit. So if you want to treat that very carefully, what you would do is to introduce a finite player game, write a finite player game, and try to show that the solution of the equilibrium of the finite player game will converge to this infinite player game limit, which is a mean field control or mean field game, depending if it's collaborative in the case of control. and competitive in the case of a min-fi game. Okay, so I said asymptotic formulation. You have also the stationary formulation. I'm not insisting too much, but simply to tell you that stationary, your mu0 is part of the unknown. That's the difference. You want the mu to be the same for all the time, starting from 0. That's why I don't like this formulation for doing reinforcement learning, because in reinforcement learning, mu0, you don't know, mu0 is given, and you try to learn the mu hat as you go. But in any case, you can prove easily in our finite space case that the optimal alpha for asymptotic min-fi game is the same as the optimal alpha for stationary min-fi game, and the same for min-fi control. So in the end, if you solve the asymptotic formulation, you have solved the stationary formulation. So I'm not insisting too much, but now we want to look at this MDP and revisit the Q function. So let's look at the min-fi game. So this is our Q function. This is exactly the same definition, except now it depends on mu. You have a given distribution mu, and you write your Q function. And the Q function as the optimal value of the Q will satisfy this will be by definition the minimum of this quantity when the mu is given. And of course the dynamics depend on the mu. And now mu is fixed, and you want to do a fixed point. And so, sorry, before doing a fixed point, you want to write an equation for Q star mu when mu is fixed. And this is our classical Bellman equation. This is a Bellman equation that I presented at the beginning, except that mu is like a parameter here. Mu is fixed, and it's a parameter of this equation, right? So now what you want to do is to update the mu as you go, right? So you want to update the population because you have new information. You want to update the population. So you do your classical update of the Q function. That's what we had before. Remember this raw Q, the rate of updating of the Q function. But now what you will do is you will update the population. You have a new observation. You want to update the distribution of the population according to your new observation. And this is why we introduce a rate of update. That's a new rate of update, which is the rate of update of the population. And this is this is the details of how you update the population with your new observation. And so all these are classical. And of course, the P is given by this transition probabilities following the RME. Well, so here we have two scales, if you want. If you look at the algorithm, you have two time scales. You have a long episode. You have the time scale of the update of Q, and you have the time scale of the update of mu. And we use the Borchardt approach to this two time scale situation to track the situation with ODEs. So now, suppose you are in a min-fi game. The idea of the min-fi game is that the population is given, is frozen, the population is frozen, and you do your own action. Because of the law of large number, by your own action, you are not changing the population. Population is very large. What you do will not change the population. So it's like you evolve in a frozen population. So how do we do that? In our algorithm, we say simply that the rate of update of the mu is much smaller than the rate of update of the Q. You update the mu less often than you update the Q table. So you introduce this small parameter, epsilon, and then following this finite difference equation, system of equation by episode, we track it by a system of ODE, and here is a system of ODE. This is the update of your mu, and this is the update of your Q, which is faster than the update of the mu. And now you can apply this Borchardt's analysis, which says now if you take this equation, epsilon goes to 0. If epsilon is very small, then this means that this should go to the fixed point of this operation. But the fixed point of this operation tells you that you have the optimal, the equilibrium Q satisfying the Bellman equation for mu given. And then you go to the second equation. The second equation is will read like this. And when t goes to infinity with a lot of episodes, this will converge to the fixed point of this. And this is exactly this equation. And that tells you that you have solved your Bellman equation. You have the optimal the optimal Q because this is a fixed point of your equation. So the conclusion is that if you can compute the Q mu infinity, take the argmin and you get the alpha. That's your Nash equilibrium. Right? It's Nash equilibrium because we were freezing the distribution, freezing in the sense that we update it much lower than the Q. Right? Okay, now if we look at the asymptotic mean field control as opposite, we have to do something a little bit differently. Sorry. So in the case of control, you don't freeze the population. When the central planners give the order to the agent, they all do the same thing. So you have to update right away your alpha. So if you were following the policy alpha, if you're following the policy alpha and you take the action A, you have to modify your policy right away because everybody is doing the same thing. So this is why we introduce this alpha tilde, which means that if you take the first action A, you have to modify your policy alpha. So now you look at your modified Q function. So the modified Q function, remember that the F will depend, the cost will depend on the mu, and the transition will depend on the mu. And here what we do, we modify the mu right away. So this is the old mu, but we modified it because the first action we took was A. The first action we take is A, so we have to modify the distribution right away. And this is what the environment will do. The environment will modify right away the distribution because all the agents are doing the same thing. And then the environment will return to you the cost, which depend on the new distribution, updated distribution. Now, we here, it's a little bit more complicated. The situation is more complicated because you update the mu at the same time. There is one direction of research. I didn't put all the literature because this is already a lot of details. But one direction of research is to put the distribution itself in the state space. So you have your state space and then you put the distribution. And then you consider it as a classical MDP on this new enlarged space. The drawback of that is that the state space was finite, but if you put the distribution, then you have an infinite dimensional space. So now you're working on an MDP on an infinite dimensional space and doing a reinforcement learning on infinite dimensional space. That's a little bit of a problem. It may be a problem. But this route has been followed by many authors in the field. We did something different. And this is in the paper that I will be citing again. We established directly a new Bellman equation for this Q, for this new Q here. And the new Bellman equation, we call it Makin-Blasov-Bellman equation because it depends on the distribution. And we worked quite hard to establish this new Bellman equation. You see, the new Bellman equation is that you have to update the mu right here and you have to update the mu right there. So there is a lot of work to establish this Bellman equation, but this is satisfying in the sense that you go back to the 60s and you try to generalize that to this new Makin-Vlasov situation. And so this is what we proved. So you have a new Bellman equation, and then this is giving you the alpha star. Okay, and of course V star is a minimum of Q star. So now, how do we compare the two? For mean field game, you have the classical Bellman equation. You freeze mu, and this is a classical Bellman equation. For the mean field control, you have a new modified Makin-Vlasov Bellman equation, which is given by this equation here, where you have to update right away your mu. So this is a difference between the two. If you look at the difference between the two here, if you formally you write it and you look at the difference between the two, what you observe is that you have this term which is like different. You differentiate the cost with respect to mu, and you differentiate the transition with respect to mu. So this is very classical in continuous space, continuous time, no reinforcement learning, mean field game, mean field control. Then when you define an Hamiltonian, you have to differentiate the Hamiltonian with respect to the measure. This is what led a lot of work, in mathematical work, in the field of mean field game and mean field control, because you have to learn how to differentiate with respect to a measure. So now you have to differentiate with respect to an infinite dimensional variable. How do you do that? This was the work of Lasserie, Lyons, Carmona, all these Carmona de la Rue, all these people who have been working hard in this area. And in particular, Lyons, one approach of Lyons was to uplift everything to an L2 space. Instead of the measure, you consider random variable in an L2 space, which has that as a distribution. Now you're in an L2 space. We know how to differentiate in an L2 space, and then you go back down. That was the approach that Lyons took, but now we have many different approaches, and we mastered that. But basically here it's very simple. It's not a differential, it's just a difference equation. And this is clear that the difference between the two is that you have to differentiate with a measure. In min-fi game, you don't, because the measure is frozen. In min-fi control, the measure moves, so you have to differentiate with respect to the measure. So this is the idea. Okay, so now for min-fi control, what you do is you want to update faster the mu than the q. You introduce this epsilon again, you write your system of equation, but now you see that the fast one is the one updating the measure, and the slow one is the one updating the q. So you redo your derivation, get an equilibrium here. So this means you have this equation, and then from this equation, the slow equation, the updating of the q looks like this, but you see you have the modified mu right there, and then you continue, you look at the fixed point of this, take t to infinity, you should converge to the fixed point, and this is your fixed point equation, and this is exactly the solution of your modified Bellman equation. So in a sense, you redo the Borka with the two scales separated to scale, and you see that you will converge to the optimal equation. So this will give you the solution for the min-fi control. Now, let me go back here. So writing an algorithm, and I will show you the meta algorithm in a minute. It's very simple. There is no, it's very easy. But my point when I started this work with my student Andrea Giuli was that, okay, you write an algorithm, but how do you know that your algorithm will converge to min-fi control or min-fi game? What is the limit? You get a limit, but how do you know that? And that was my starting point. I wanted to write a paper with a warning. Be careful, because sometimes you don't know what you are computing, and you have to be a little bit more careful than that. That was a starting point, and then this is what I will present in a minute. So this is a classical scheme. It's the same thing as all in the textbook, except that you have the distribution. You have to take care of the distribution, and this is the environment taking care of the distribution. It's not the agent. The agent doesn't even look at the distribution. The agent look at the value of the cost, the new x, take an action, get the value of the cost, but the environment depends on the distribution, and this distribution is updated as we go. It is updated slowly if it's a min-fi game, because all the agents are competitive. It is updated fastly if it's collaborative, min-fi control, because all the agents are doing the same thing at the same time. So it will depend really on the kind of games that we are trying to solve. So this is again what I just said. Now let's look at the meta algorithm. I don't want you to read all the lines, but let me point. So you initialize uniformly, basically on the state space. It's a finite state space. You use an epsilon greedy. You see you have the epsilon greedy, which is here, to explore the space at each step. But what is important here? What is important is the update of mu. So you update the mu with a rate rho mu. So that's your update of the mu along the trajectory. For instance, if it depends only on the mean of the distribution, in the example that we have, if we depend only on the mean, you update the mean, right? That's what we do. You may not have to deal with the full distribution. You may deal only with the mean if it depends only on the mean. And then you take your action using an epsilon greedy policy, and you observe the new cost, you observe the position, and you update the Q, again, following our Bellman equation, but you have the raw Q. So, and you have to stop, you have to give some criteria to stop the algorithm, but what is important here is raw mu and raw Q. So if you implement this algorithm without knowing anything about raw mu and raw Q, you don't know what you are computing. And actually, if raw mu and raw Q are less the same, for instance, then it may not converge actually. So this is where the analysis is very important. The analysis that we proposed before, that the choice of rho mu and rho q will tell you what you are doing, right? So, and this is what I want to put the focus on is those learning rates. So this is a learning rate for q, and you see it's 1/1 plus k. Of course, it depends on x and a, but let's say k to some power omega q, and this is 1/1 plus k to some power omega mu. And those two numbers have to be chosen, right? So the omega q is between 1/2 and 1 because we do this stochastic approximation. And so depending how you choose omega q and omega q, you get min phi game or min phi control. In our example, we'll do 80,000 episodes. And let me show you the rate. So for instance, in the case of min phi game, we'll take omega q is 0.55 and omega mu should be larger because the rho mu is smaller. So this we point in our application, we take 0.85 and to have this relation. In the case of min phi control, we will do the opposite. We take omega mu to be 0.15. This doesn't need to satisfy the stochastic approximation. So so we've in this case. So these are in the log plot the comparison of the two rates. So this is a q, and this is the mu in the case of min phi game, and in the case of min phi control. So let's do a benchmark model. So now here we have a problem because if you want to do a benchmark model, it means that you need to have a solution. So either you find a good problem with a finite space, finite action. Actually, there is one, but the solution is not explicit. You have to compute it numerically. There are examples with finite space, of course, in particular in the area of cybersecurity, but I don't want to go into that. So what we did a little bit differently. We look at a continuous time, continuous space model for which we know a lot of things. It's a diffusion world. So we're in a diffusion world with Brownian motion, and we know basically how to solve the min phi game. If it's linear quadratic, we know how to solve. So this is what we are taking, and then we will discretize that. We have a continuous time, continuous space model for which we will know the solution explicitly for min phi game or min phi control, and we discretize it to implement our algorithm. We put bins and we count the bins. And so I'm not getting into all these gory details, but this is what we do. So the evolution, so this is your transition. It's a diffusion. You have a constant volatility here, and you choose your drift. The control is a drift of the diffusion, right? So what is called B usually, which may depend on X, on alpha, and mu. It just depends on alpha. Very simple. D equals 1, and then we want an interaction. So the interaction will be through the mean of the distribution, only the mean of the distribution in the cost function. So this is your cost function. So let me show you. So you have the quadratic cost you pay for controlling your diffusion. You may want to be the state to be close to the mean. Let's say if C2 equals 1, this is mean reverting. You want to mean revert to the mean of the population. You may have a target value. You want this to be close to a target value, and maybe you want the mean to be close to 0, let's say, or 0 another value, but let's say 0. You want to control so that the mean is close to 0. So this is typically we get all the effects in this form. In particular, this will be important to have a term like that because it will make the difference between min phi game and min phi control. You have problems for which the solution of the min phi game is the same as a solution of the min phi control, and we want to be in a situation that they are different. So we can, and this is part of make this different. Okay, so for this problem, first we can solve this problem. This is linear quadratic. You can write the solution of min phi game of min phi control, right? So we have a benchmark. We know where we are going. Since it's linear quadratic, the optimal control is linear. Right? The value function is quadratic, the linear control is linear. So this is a linear control. On the left is a min phi game with the parameters that I told you. And so this is our target, this is our control. This is a computed control. And you see that we are learning well. So this is a little bit average over 10 runs. We are learning well the control. No, we don't, but this is not very important, because if you look at the distribution, we are learning the distribution at the same time. If you look at the distribution, this is outside of the support of the distribution. We never go there, basically. So we learn very well the control within the support of the distribution. That's what reinforcement learning is doing. And don't forget that the benchmark is continuous space, infinite space, continuous time, and we are discretizing everything. So this is mean field game. Mean field control is a little bit more noisy. We learn the control. There is a difference between the two controls. They have the same slope. When you compute, they are the same slope, but they have different intercept. So we learn the control on the support of the distribution, but you see it's a little bit more noisy at the level of the distribution. This can be understood because here the distribution is frozen, it moves slowly. Here the distribution moves all the time. So you get more noise. And so you can fix that by averaging a little bit. So the next picture is the same, except that we average over the last 10K episode. So the distribution is less noisy, and you see that we learn the control quite well. So I don't want to insist too much on that. We learn also the value function, but I don't want to get into that. More importantly, here's a paper. So the paper has been published in Mathematics of Control, Signal and System, MCSS, and it's on the archive, so you can get to my webpage and you find it easily on my list of publications. So this is, and so what is important here? What is important is this: if you write the algorithm and you pick rho mu and rho q, or the omegas, let's say the same, both of them 0.55, you will not converge to any, or maybe you will converge to something which is neither the mean field control, neither the mean field game. So someone who doesn't know what he's doing may not compute the right quantity. So this is the main lesson of this thing, and we provide an algorithm which can do both at the same time, depending how you choose your parameter, your learning rates. Okay, so time is flying. There is a second paper that we wrote after that, same authors with Andrea and Mathieu Laurière. And this is to appear in this handbook on machine learning for financial market, edited by Cambridge University Press, by Caponi, Agostino Caponi, Charles Albert Lehal. And this paper is to appear, and it's also on my webpage on the archives. So this, what is interesting here is that we generalize to what is called extended mean field game. First, finite time instead of infinite horizon. This will be finite time. For application, sometimes finite time is very important. And extended mean field game in the sense that it's mean field game also on the control. It's a mean field game of action. It's not only a mean field game of the state, it can be a mean field game of action. And I will give you an example in a minute. And so application. So this is done in this paper. So what is extended and finite horizon is easy to understand. The only thing is that now is everything depends on n. You have a finite horizon. What is important here is that this nu is a distribution not only on the state, but on the state and action. It's a joint distribution on the state and action. And you see that the terminal condition depends only on the marginal on the state. At the end, you don't want to depend on the distribution of action because the action doesn't do anything. Right? At the end, you don't control anything. Okay, so you redo everything. Everything will depend on Tn now. So time is flying, so let me go a little bit fast. And for the mean field control, is the same thing, except that you update your nu, the distribution depending on the alpha that you take, and you have your value function. So everything is basically the same, except that it's finite horizon and it's a distribution of state and control. So now the reinforcement learning part is given by the mean field game Bellman equation. So the Bellman equation now has a terminal condition, and this is your recursive Bellman equation. The Q depends on n, depends on time now. That's a new part. So you have another dimension now. You have Q, X, and A, but also an n and the time, right? So it's a bigger problem. And for the mean field control, it's the same thing, except that you update right away this thing, and you have this extended or modified Bellman equation, Mac-inverse of Bellman equation. Okay, so you have to redo all this. You have to write the code. The code is basically the same thing, except that the Q depends on N. That's the main difference. Q depends on N, and you have to update at the same time the pair of distribution, the couple of distribution of the state, distribution of the control, and then you do the same thing, and you have the same relation between the row nu and the row Q. Those two rates have to be updated depending on what you want to do. So let me give you a couple of examples. One is from Mini Wang from the 2013, I think. So this is the capital accumulation problem. So this is the capital of the European, you have an agent. It's in discrete time. This is in discrete time. So this is the control. The control is a fraction, the fraction of your investment. So let me give you more. So this is a production function. You have the production function which depends on the distribution of all the action, distribution of all the action of the other player. So it's a mean. It's the mean of the distribution of the other players. It has a noise and as a function here, and this is the fraction that you invest, fraction of your wealth that you invest. And so you see now it's a distribution not of the state, but of the action. That's why it's an extended mean field game problem through the mean. So this is a mean field term, and W is a noise. Okay, so of course, this is the fraction that you invest. It cannot be bigger than what you have, right? So the alpha, the support of the alpha is 0x, your own present capital. And then what you do is the rest, the one that you didn't invest, you consume. You consume what you are not investing. So you consume as you go, and you invest the rest. And so then that technical condition on the function G and everything, so that the problem will make sense. I'm skipping that, but what is important is what you want to do. So this is an example where all the conditions are satisfied. But what you want to do is that you will accumulate. Now you will accumulate consumption. So you want to maximize in this case. This is maximize of consumption. So you have a rate of discount. You accumulate the consumption, and the consumption has a utility. So this is your consumption, and you have a utility. And in this case, we take power utility, like exactly in the paper of Mini Wang. And you have a power utility which is given like that with some given gamma, right? So, and you want to maximize this accumulated consumption, right? So we are in a finite horizon, time dependent, and extended mean field game because it depends on the distribution of the action. So mean field game in the case of linear quadratic, we can solve it explicitly. So we are in this case here power, and we take this function. So this is linear quadratic again. We can solve it, and it's not linear quadratic, but it's linear, and the control is linear. Is given by this formula, and you can compute the phi t recursively. I'm not showing you the details, but this can be computed. In a mean field control, it's a little bit more complicated because here you have the expected value of the distribution of your alpha, and this cannot be solved explicitly. Amazingly, this one can be solved. This one cannot be solved explicitly, but it can be solved numerically. You have a numerical solution of that, and this is what will be our benchmark. Our benchmark is a formula here, but in this case is numerically derived independently, right? So our example is where t equals 2, so 0, 1, 2. You have 2 periods of time. And again, you see, we take about the same values for this mean field game and mean field control for the omegas, but the choice of omegas. So here is the answer. So on the left is mean field game. So mean field game is the linear control. So that's the blue triangle is the formula, the control. And you see that the stars are quite well aligned at time t equals 0. This is at time t equals 0. And that refers to the mean field control. And this is right panel. In the right panel, you get the mean fee control, which is computed, the red square are computed numerically, and the stars is what the reinforcement learning is learning. You see that you are learning correctly everything. At time 0, you're learning the control for mean fee control, and you are learning the mean fee game right there. So this is at time 1 in between. So you're learning this, it's a little bit not as precise, but you are learning. And again, you are learning the mean fee control. And of course, at time 2, there is nothing to learn, but you will learn that there is nothing to learn. This should be 0. You don't control anything because it's the end, right? It's the end of the period. Okay, so this was one example. Let me give you a couple of minutes, a trader's execution problem. I will go very fast because time is running. Trader's problem, I don't want to give you more results, but I want to focus on what kind of problem we can address. So the trader, you have the inventory of the trader. So the inventory, so you have a sigma, which is your fluctuation in the inventory, your own fluctuation, and alpha is your control on the inventory. You sell, you buy, you sell or you buy, right? The price of the asset has its own noise, but it has an impact from all the trades. It's impacted by all the trades. Gamma is this coefficient of impact, and so we will choose some. So this is how the trades of everybody will impact the price of the asset. And of course, you have an amount of cash, so everything is self-financing. This C alpha, the amount of cash C alpha, and this is a cost of trading. So basically, this will be quadratic in the application. So this is your cost of trading, and the wealth by self-financing properties given by this. You compute the differential of the wealth. So this is classical stochastic calculus that you apply here. But what is important is what you want to optimize. So this is the cost of carrying the inventory. So it's a running cost of carrying the inventory, and this is your terminal cost of the inventory minus the value of your portfolio, what you will be selling. So this is what you want to minimize. And if you rewrite it like this, and you pick a particular F. So this is the F, the cost of trading, the cost of inventory, and the price impact. And as a model, we take this very well-known Greentree linear price model. And so this is the linear price, it's linear in X. That is that model. We take quadratic cost, quadratic inventory at the end, and we minimize on alpha. And so this is a linear quadratic problem, except that this is under control. We know how to solve that. There is a solution either for mean fee game and for mean fee control. So I will not show you how the algorithm is performing, because it's basically the same as the one I showed at the beginning with the example with the benchmark of linear quadratic. It behaves exactly the same. So I'm not showing you that. Instead, if you go to the paper, you will see the solution, all the solution on that, and so I'm just giving you again the two papers that I talked about. The first one here, sorry, the first one is right there. I'm sorry. This is the second one with extended mean fee game application to finance in this handbook, and I want to recall the Infinite Horizon paper. The first one I talked about is on the archive. The second one is the second one is this one here. It's also on the archive. And now I want to mention a very new, very recent work. I have 2 minutes because I started late of 2 minutes. If you give me 2 minutes, I will conclude. I want to mention this new paper, which is on the archive, where now we say, but look, I mean, if we look at the algorithm, this is why it's interesting. It's not from the point of view of the mathematics point of view of the algorithm. We design an algorithm which either can do mean fee game or mean fee control, depending on this row, the ratio of the row. But the algorithm, if you write an extra line of the algorithm, you could do two things. You could do 3 rates. you could have a mu which is updated slowly, the Q, and a mu which is updated fastly. So the algorithm is designed to do much more. It could do the two things at the same time with 3 rates, right? But then the question is, oh, nice, very nice. But what is that problem? It corresponds to what? It's not a min-fi game, it's not min-fi game. And this paper identify what this is, and this is extremely interesting. I think it's extremely interesting. This is what we call mean field control games. Mean field control game, and it is a case where you have, instead of having competitive players, you have competitive groups of players. The groups are collaborating, and those groups are competitive. So, and this is very interesting. That I want to mention this paper because it's a new kind of game. It's a very interesting new kind of game, and the algorithm can do exactly what it is designed for. So we are working on this paper. This is very interesting. I don't want to talk more about it, but this is a new development which will stay healthy. I will try to. I could do 1 hour, which is good with my voice, and I would be happy to answer any question. Thank you.
Thank you very much, Professor Jean-Pierre Fouque. It was a very nice talk. So I would check if there are any questions from the audience. Please unmute yourself and can ask. Okay, I mean, in the meantime, by the time a question comes, I just want some clarification about that, asset price dynamics. May I request you to go to that that optimal consumption problem, where yes, so there was an equation dx. Yes, I was talking about this equation.
This one?
Not this one. After this, the dxt is equal to alpha xdt.
Oh, the trader's problem.
Yes, trader's problem. Yes.
The trader's problem. Okay.
Yes, this one, alpha t dt plus sigma dwt. So yes, so yeah, I'm interested in I'm studying this type of problem where traders are playing these things, and I mean basically microstructure of the market. But there, what I have observed is that these models are not ensuring positivity of the assets. So could you please, explain, see, for example, this particular equation here, the positivity of X is not ensured, right?
Yes.
Right?
So this is a model where the asset follows a Brownian motion. And this is a typical model when you are in a short time. Capital T is short. So the probability that this becomes negative is extremely small. That's an approximation, right?
Okay, I understand. Okay.
The stock is a Brownian motion, not a geometry Brownian motion, but a Brownian motion. This has been used a lot in this area because
this
T
is
like
standard.
1 day.
Yes, correct. But I did not get the clarification that why is it taken. So that's why I just wanted to get clarification. Thank you.
That's correct. If you take a geometric Brownian motion right there, then you are losing the explicit formulas. That's it.
Okay. Okay. I have another question. That is, when you showed that in that optimal consumption problem. So there, in that, was there any study about Euler equation under the optimal consumption?
So
Yes.
what is exactly the question? I'm not sure I understand the question. But
okay, the question is that in that problem of finding out optimal consumption, so I mean that is being studied by this mean field control. Now question is that when you get that optimal consumption, that I mean as a solution of that problem, maybe the alpha star mu star, where so then under the optimal consumption, I mean, is there any Euler equation? Like Euler equation says that it compares between two scenarios. One is that saving now and consuming later. Another is that consume now, okay, and then compares between these two scenarios and says that they must be equal. So when the consumption is optimal. So my question is that for these type of problems, this is very complicated, of course, because that Euler equation is doable for much simpler scenarios. But for these cases, were there any such study of Euler equation?
I don't know, but I would say this will be difficult. First, it's time dependent, so it's not now, and it's not one per model. It's time dependent. So what is the meaning of selling now or consuming later? What does it mean exactly? I don't know. But if you formulate the problem like that, you have an optimal alpha. So you find an optimal alpha. So and the optimal alpha, let's say for instance in this case, the optimal alpha is given by linear, for mean field game is given by a linear formula. So if you deviate from that, you won't be optimal. So that's my answer. But I don't know about the equation that you're mentioning for this case. I don't know.
Okay. Yeah, thank you very much. Yes.
I have a question.
I see. Yes.
Yeah, there are some other questions, I think, from the audience.
Professor Fouque, very nice to meet you virtually. I'm Indranil. So I have a question, like when you showed the dynamics that you just showed, like which is the Brownian motion dynamics, and you use that for the benchmark model as well, right?
Yes.
So my question is it, that one, the previous one, right here. So is it worth considering the jump term by any chance, like the Poisson term?
Yes, of course. I mean, you can. I mean, we use that only. The first case was just a benchmark, so we were interested in explicit solution.
Yes.
Do you have explicit solution when you have jump? We'll have to think a little bit. If you have explicit solution when you have jumps, maybe because we were interested in explicit solution. So it's not that we are trying to sell the model, right?
I see.
It's really to get something where we have explicit solution, and now we do reinforcement learning, where we suppose that the agent doesn't know the model. Right? It doesn't know the model, it just observes the new position. And so the goal was not to get the most fancy, the fanciest model. But of course, in reality, you may have jump in the dynamics, why not? And now you have to say, what do you control? Are you controlling the jumps? Are you controlling only the drift? So you have to be more precise. And yeah, of course, I mean, this can be done. The algorithm should not look at that. It doesn't matter. The algorithm doesn't matter. You have dynamics, and then you follow the dynamics. That should work. But then, so the algorithm will find you some optimal alpha. But how do you know if it's the right optimal alpha? You have to believe in your algorithm. I believe in the algorithm. So put any model you want, any dynamics you want, you put it in the algorithm, and that should work under some ergodicity assumption. It needs some ergodicity and things like that to work. But under some nice assumption, it should work. Yeah, why not? Yeah.
Sure. No, thank you very much. It's a wonderful talk.
I want to mention something else also. We use as a benchmark continuous time, continuous space diffusion. The direction of research that we are following now is to get out of this Q-learning and go with actor-critic. This actor-critic approach or stochastic gradient descent to deal directly on the continuous space. So this is what we are doing now. It starts working well. There is a lot of things to tune in the algorithm, but we try to get away from the Q-learning, which is really finite space, finite action. So for this kind of problem, it should be treated with an actor-critic approach or value-based function.
Thank you.
Yeah. Yes, thanks. Okay, is it late for you? I mean, what is the time in India?
In India, it is 8:15 p.m.
8:15, so it's almost 8 in the morning here, so I will get my breakfast now.
Yeah, and I mean, it is really, you know, I mean, we were really grateful that with your this you know, unwell health, you still agreed to continue.
Okay, thank you so much for inviting, and great continuation. Thank you.
Okay, thank you.
Thank you.
Okay,
Bye
so
bye.
we end the
Good
session
evening.
then. Bye bye.
Bye.